Hello everyone. Welcome to the problem solving session for the week 6 of the course Computational Competitive Algebra. Let's start by summarizing the topics of week 6. Then I will come to the problems related to those topics. Let's write the keywords of the topics of week 6. So in week 5, we were looking at associated primes, and in week 6 we started with some more properties of associated primes, like if we have a radical ideal I, then the quotient r mod I, it cannot have any embedded primes, and some more other properties. And then we have defined saturation of two ideals in a Noetherian ring. So saturation of ideals. Then we were studying basically these saturations. Then in Macaulay 2, we were doing some computations, uh, that how to compute associated primes using those saturations. So computation of associated primes using saturation. Then after this, we were studying how to compute the saturations. So computation of saturations in Macaulay 2. So computation of saturations. Then we move on to some geometrical topics, like morphisms of the prime spectra or the maximal spectra. So I will just write morphisms of spectra and the fibers. So we are looking at the fibers. So it is like if we have a ring homomorphism phi from R to S, then it will induce a continuous function from spec S to spec R. Then if you take a point here, so you can talk about the inverse image of this point. This this inverse image is called the fiber of phi over P. So that is what we were studying in the last two lectures of week 6. So this is about fibers. Then we have also seen a bunch of examples in which we have calculated the fibers. So these are the main topics of week 6. Let's start by solving some problems based on these topics. So the first one is uh, so this is from the practice problem sheets, and the next problems will also be from the practice problem sheet. So let K be an algebraically closed field. So you can take the complex numbers, for example. So K be an algebraically closed field. Then compute the irreducible components of z of I, where I is the ideal generated by x square y comma xz comma yq, which is in the ring k x y z, the polynomial ring over k in three variables x, y and z. So we have this polynomial ring, and we are given an ideal in this polynomial ring. Then z of I is basically the zero set, which is subset of k power 3. So this is k power 3 is equipped with the Zariski topology. So we can talk about, so this is a closed subset. So we can talk about the irreducible components of this closed set. So let's do it. So first, let's recall the definition of z of I. So z of I is basically, in this case, all a belongs to k power 3 such that f of a is equals to 0 for all f belongs to the ideal I. So all f means all polynomials belongs to ideal I. So if f is a polynomial in I, so it is subset of this ring k x y z. So we can think k as a function from kn to k, right? How? By evaluating at just by the evolution function. So this is the definition of z of I. So this is basically the set of all common zeros of polynomials in I. So we need to find the irreducible components of z of I. So let's do it by two different approaches. So let's I will first do it by using the primary decomposition and by using the Hilbert-Nunn-Stellenzer. So first let's find the primary decomposition of this ideal I. Because this is a monomial ideal, we can find the primary decomposition easily. So let's do it. So okay, so yeah, so let's find the primary decomposition of the ideal I. So our I is basically x square y comma xz comma yq. Now x and z are basically relatively prime. So we can write this thing as x square y comma x comma yq intersect with x square y comma z comma yq. Now we have x here and x square y here. So x square y is irredundant. So this is basically x comma yq intersection with x square y comma z comma yq. Now this is a primary ideal. So this is a primary component. So we need to break this part now. Now here x square times y. We need to break this part. Here x square and y, these two are relatively prime. So again we will use the same trick. So we can write this as x comma yq intersection x square comma z comma yq, again intersection with y comma z comma yq. Now here y is here, yq is also here, so yq is irredundant. So we can write this as x comma yq intersection x square yq z intersection y comma z. So this will be the primary decomposition, because these are primary ideals and none. So this is the primary decomposition. So what is the set of all associated primes of R mod I? So associated primes will be radical of these primary ideals. So y comma z is itself prime, so its radical is so radical of x comma yq is basically the ideal generated by x comma y, and radical of this is m primary ideal, maximal ideal, x square yq z. This is basically x comma y comma z, and the third one is itself radical because it is itself prime. So this is x comma y, x comma y comma z. So I will write these things here, and ideal generated by y comma z. So these are the three associated primes. So we can write, so if we take radical of I, then it will be radical of x comma y q intersection uh, radical of x square yq comma z intersection radical of y comma z. So this is because if we take radical of ii, this is same as intersection of radical of ii. So these things will commute. So radical commutes with taking intersections. So we can write this radical of I as x comma y intersection x comma y comma z intersect with y comma z. But uh, so now we need to find z of I. So we know from the properties that z of I is same as z of radical of I. So this is same as z of x comma y intersection x comma y comma z intersection ideal y comma z. Now if we take the intersection out, it will become union by the properties we have seen in the earlier lectures. So this is basically z of the ideal x comma y intersection will become union z of x comma y comma z. This is z of y comma z. So x comma y and y comma z are prime ideals. So these zero sets are already irreducible. This is also irreducible. But is this the irreducible decomposition? Because uh, observe one thing, that this term is irredundant. We can remove this term because x comma y is subset of x comma y comma z. So that will imply z of x comma y comma z will be subset of z of x comma y. So this term is already contained in this one, and it is also contained in this one. So we can remove the middle one. So we can write this as z of x comma y union z of y comma z. Now these two cannot be removed. So this is the irreducible decomposition. So this is the irreducible decomposition of zero set of I. So this thing I have done by using primary decomposition. Now what actually we are doing? So I will put that as a remark. So we have already solved the problem. Now let's do it by using some easier way. So if we write z of I, so its irreducible decomposition is basically the union of z of p, where p is in the set of all minimal primes of R mod I, right? So you just recall it from the lectures. So we need to find just the minimal primes of R mod I. That means all minimal primes which contains I. So we need to find minimal primes of R mod I. Now let P be a prime ideal of R such that I is subset of P. So from that we can conclude, so the ideal is x square y comma xz comma yq. This has to be subset of P. So this implies x square y xz yq, all these three elements belongs to P. Now P is a prime ideal and yq belongs to P. That will imply y belongs to P. So that will imply y belongs to P, and xz belongs to P. So that will imply either x belongs to P or z belongs to P. So x belongs to P or z belongs to P. And since y belongs to P, so this element clearly belongs to P. So we will not get anything new from this. So we have these two statements. So from this we can say that y is always belongs to P, but we can have either x belongs to P or z belongs to P. So we can have only two cases. So either x comma y is subset of P, or y comma z is subset of P. Now what does it mean? So if is a prime ideal which contains I, then P must contain either this ideal or this ideal. So these two are the minimal primes. So minimal primes of R mod I is x comma y and y comma z. So this will give the irreducible decomposition of z of I as z of the ideal generated by x comma y union z of the ideal generated by y comma z. So in this way it is very easy to compute. One more thing, if you don't want to compute the minimal primes by using hand, so you can use the Macaulay 2. So there is a command in Macaulay 2 which can be used to compute the minimal primes. So there is a command to compute the minimal primes of a monomial ideal in Macaulay 2. So what is the command? So the command is it is just minimal p is bigger, minimal primes, then you just write the ideal here. Let's say ideal I. So you just define the ring as some field q comma q x comma y comma z. Define the ideal as ideal. Then you just write this command. Then it will give you the minimal primes. So in Macaulay 2, you can also compute the associated primes. So in place of minimal, you just write the associated word. Okay, so let's move on to another problem. So problem number 2. So let R be a Noetherian ring R be a Noetherian ring and I be an ideal of R. Also let A belongs to R. Now if I colon A is same as I colon A square, then so that uh, the following things. So the first one is I is basically I colon A intersection I plus the ideal generated by the element A. So this is the first one. And second one is I colon A is same as I colon A power M for all positive integer n. So what is given is we are given an ideal I in a Noetherian ring R and A be an arbitrary element of R. So A be an arbitrary element which has the property that I colon A is same as I colon A square. Now using this information we have to prove two things. The first one is the ideal I is same as the ideal I colon A intersect with the ideal I plus ideal generated by A. So this is the first one. And second one is I colon A is same as I colon A power M for all m greater equals to 1. So this will give you that this is same as I colon A power infinity, the saturation of I with respect to A. So let's prove this one by one. Okay, so let's start with the first one. So we need to prove that equality of these two ideals. So as usual, we will use the usual technique. One is subset of the another. So one inclusion is always trivial. So observe that I is subset of I colon A and subset of the ideal generated by I. So ideal generated by A plus I. So this will imply I is subset of their intersection. So I colon A intersection I plus ideal generated by A. So one inclusion is trivial. So let's prove the other inclusion. So let X belongs to I colon A intersection with I plus ideal generated by A. Now we need to prove that this X belongs to I. Then that will complete our proof for the first part. So what can we say from here is X belongs to I colon A as well as X belongs to the ideal generated by A plus I. So from this we can say AX belongs to I, and we can write X as some Y plus R times A. So for some Y belongs to I and R belongs to R, because X is an element of this ideal I plus ideal generated by A, so X must have this type of form. Now AX is in I, so if we multiply A with X, so that is in I, so this implies AX, which is equals to AY plus R A square, this is in I. So AX is in I, but Y is in I, so AY is also is in I. So this implies AX minus AY equals to RA square. This is in I because AY is in I. Now this implies RA square is in I. So R belongs to I colon A square. But what is given? So given is I colon A square is same as I colon A. So this is same as I colon A. So from this we can write R times A is in I. So our X, which is Y plus RA, Y is already in I and we have proved RA is in I. So their sum must be is in I. So this implies X is in I. So this proves that. So we have taken X from this right hand side and X belongs to the left hand side. So this implies I equals to I colon A intersection I plus the ideal generated by A. So this proves the first part. So we have proved the first part. So now the second part. So we have to prove that if we take I colon A power m, then that has to be equal with I colon A for whatever positive integer m. And we have to use this fact. So the second one. So first observe that so first thing is I colon A is same as I colon A square. So that will imply I colon A square equals to I colon A power 4. This is equals to I colon A power 8 and so on. So this means I colon A is equals to I colon A power 2 power m for all m greater equals to 1. And also note that we have an ascending chain of ideals I colon A, which is subset of I colon A square, which is subset of I colon AQ, which is subset of I colon A power 5, sorry, I colon A power 4, and subset of so on. And this, okay. And this ends with the saturation because we are in a Noetherian ring. Now, this equality is given, and from this we have proved that this is equal with this. So these two ideals are equal. So whatever in between, that has to be equal. Similarly, here we have I colon A power 8. So this thing is equal with I colon A power 4. So whatever is in between, that has to be equal. So this implies I colon A is same as I colon A power M for all m greater equals to 1. So that is just an observation. So this proves the second part also. So we have proved the both parts of question number 2. Okay, so let's move on. So the next is problem number 3. So again, let R be a Noetherian ring R be a Noetherian ring and I be an ideal of R. So again the same setup, R is a Noetherian ring and I is an ideal of R. Now suppose the ideal I is radical. Suppose I is equals to its radical. Then show that uh, for every A which is in I, which is in R minus I, the ideal I colon A, it is also radical. Okay, so what is the question? So given R is Noetherian and we have an ideal I which is radical, then for all A belongs to R minus I, the ideal I colon A, it is also radical. So this is what we have to prove. So this problem is actually very straightforward, but still let's do the proof. So let A belongs to R minus I. Then we have to prove I colon A is same as its radical. So one side is clear. So clearly I colon A is subset of its radical. So we need to prove the other way. Means radical of I colon A is subset of I colon A. So let x belongs to radical of I colon a. Now that will imply some power of x is in I colon a. So for x power n is in I colon a, for some n greater equals to 1. Now that will imply a times x power n is in I. But I is an ideal. So if we multiply this term with a power n minus 1, so that is also in I. So a power n minus 1 times a x power n is in I, because I is an ideal. So this implies ax whole power n is in I. So some power of ax is in I. So that will imply the element ax is in the radical of I. And radical of I is same as I. So that is what is given. So this implies x belongs to I colon a. So we started with an element x of radical of I colon a, and we end up with x belongs to I colon a. So this implies radical of I colon a is subset of I colon a. And this implies I colon a is itself a radical ideal. So this completes the proof for problem number 3. Okay, so let's do the next one. So this is problem number 4. So again, let R be a Noetherian ring. So R be a Noetherian ring, and J be a P primary ideal. So R is a Noetherian ring and J is a P primary ideal. Then for every A is in R minus P, the saturation of J with respect to A is same as the ideal J. So R is a Noetherian ring, J is P primary ideal. So J is P primary, that means associated. So J is a primary ideal, and associated prime of R mod J is basically the singleton set P. So what we have to prove is for every A which is not in P, if we take the saturation of J with respect to that element, then that saturation has to be equals to J, has to be equal with J. So this is also not difficult, but let's prove this. So since R is Noetherian, so since R is Noetherian, there exist exists a positive integer, so actually j colon a subset of j colon a square and dot dot so on, this is an ascending chain, and j colon a power infinity is basically the union of all this ascending chain, but we are in a Noetherian ring, so this chain has to be stabilized at some point. Means at some point, after certain stage, all the ideals are same. So let's take that stage to be m. So there exists a positive integer m such that the saturation of j with respect to a is same as j colon a power m. So after uh, a power m, all ideals are equal, and this is our saturation. Now clearly j is subset of j colon a power m, which is our saturation. So one side is clear as usual. So we need to prove the other inclusion. So we need to prove this reverse inclusion. So how to prove the reverse inclusion? So we will use the contrapositive statement. So claim, so we need to prove that j colon a power m is subset of j. So we will show that if x does not belongs to j, then x cannot be in j colon a power m. So this is the contrapositive statement to prove this inclusion. So let x is not in j, then we have to show x is not in j colon a power m. Now for contradiction, suppose x is in j colon a power m. Now what that means? So this implies x times a power m belongs to j, but given is x is not in j, so that will imply some power of a power m is in j. So because j is primary, we can say this thing. So here actually we are using one definition of primary ideal. So I will write it here. So j, an ideal of a ring R, is called primary if xy belongs to j implies x belongs to j, or y power n belongs to j for some n. So this is equivalent definition of primary ideal. So you may try to prove it or may try to see it from standard textbooks. So we will use this definition. So here x is not in j, that will imply the some power of the other element has to be in j. So this is uh, for some positive integer n. So this implies a power mn belongs to j. and J is P primary. That is what given. That is what is given. But A is not in R minus. Sorry, A is in R minus P. So J is subset of P. So this implies A power. So this implies A power Mn belongs to P. But P is a prime ideal. So this implies A belongs to P. But this is a contradiction because we have taken A from R minus P. So this is a contradiction. So we have got a contradiction. So that means what we have assumed is wrong. So we have assumed that X is in J colon A power M. So thus X cannot be in J colon A power M. And this implies J colon A power M has to be subset of J. And this implies J colon A power M uh, equals to J. And J colon A power M is same as J colon A power infinity, which is the saturation of J with respect to K. So this is same as J colon A power infinity. And this completes the proof. So this is also quite straightforward, not much difficult. Yeah, okay. Okay, so let's do the other problems. So problem number 5. So let R be a ring. So R is any ring. Any ring means commutative ring with identity. And M be an R module. Now suppose N1 up to Nr subset of M are R submodules. Now let N equals to the intersection of N1 dot dot up to intersection with Nr. Then so that there exists an R sorry an injective R module homomorphism. There exists an injective R module homomorphism. So let's say phi from M mod n to direct sum of these modules. So direct sum of the individual quotient. I is running from 1 to R. Okay, so first let's try to understand what is given and what we have to prove. So N is a ring. N1 up to Nr are submodules of an R module M. And N is the intersection of those submodules. Then we have an injective module homomorphism from this quotient M mod the intersection to this direct sum of the individual quotients. So let's prove this. So to prove that this is an injective R module map, so what I will do, so I will use the first isomorphism theorem. So let's define phi from M to this direct sum of M mod Ni, where I is running from 1 to R, by just, so what is the image of phi of M? So it is just the natural, we just combine the natural homomorphisms. So first one is M plus N1, this quotient. Second one is M plus N2, this quotient, and so on. The last one is M plus Nr. So we are combining the natural uh, homomorphisms or canonical maps from M to its quotient. So then, so you can check it that it is a R module homomorphism. So it is actually very clear. So clearly phi is an R module homomorphism. Now, what about the kernel of phi? So what about the kernel of phi? So kernel of phi is basically all those elements of the domain which are mapping to the zero element. So this is set of all those elements of M such that phi of M is mapping to 0. So here 0 means the 0 tuple. So if we write it more clearly, then it is basically all those elements of the module M such that, uh, so what is phi of M? So let's write it down. So it is M plus N1 comma M plus N2 comma dot dot so on M plus Nr. This tuple is same as the 0 tuple. So here the 0 means uh, 0 in this quotient modules. So this is same as all those elements of M such that M plus Ni is same as 0 plus Ni. So here 0 means 0, 0 quotient, 0 plus Ni. So for 1 less equals to I less equals to R. And by the properties of quotient, this is same as M belongs to M such that M belongs to Ni for 1 less equals to I less equals to R. Now what is this set? So all those M in M which is also in all the submodules Ni. So this is basically N1 intersection N2 intersection dot dot so on with Nr, and that is what our N. So this is same as N. So our kernel is the submodule N. So by first isomorphism theorem, so by the first isomorphism theorem, the map phi induces an injective R module homomorphism, let's say phi bar, from R mod kernel phi, which is say, sorry, not R. So M mod kernel phi, which is same as M mod N, to this direct sum of this quotient M mod Ni, I is equals to 1 to R. So this is fairly easy. So one thing we can conclude it from this injective map is that, so let's put it as a remark. So since phi bar from m mod n to direct sum of m mod n I equals to 1 to r is injective or 1 1, so the associated primes of the left module is subset of the associated prime of the right hand side. But what about this set, is direct sum? So since it is direct sum, this is same as union of associated primes of the individual modules. So here the individual quotients. So associated prime of m mod n is subset of union of associated primes of the quotient m mod n I for I equals to 1 to r. So this is one fact which you can try to remember. Okay, now let's do the next problem. So this is problem number 6. So okay, so let phi from cxyz to c of t be the ring map defined by x is mapping to tq, y is mapping to t power 4, and z is mapping to t power 5. Then so that kernel of this ring map is the ideal generated by xz minus y square, comma xq minus yz and x square y minus z square. So we are given a ring map defined by this: x goes to tq, y goes to t power 4, and z goes to t power 5. So we need to prove that kernel is this ideal generated by these three polynomials. So you can do it by Macaulay too by using the known commands, but let's try to do it by hand. So let I be this ideal xz generated by xz minus y square, comma xq minus yz, comma x square y minus z square. Now then, so if we take image of these three polynomials, so where they are going? So phi of xz minus y square is same as phi of xz minus phi of y square, and phi of xz is basically tq times t power 5, and phi of y square is basically t power 4 square. So this is 0. So similarly, you can check that phi of the other generators yxq minus yz, this is 0, and phi of x square y minus z square, this is also 0. So all these three polynomials is in the kernel. So this implies I is subset of kernel phi. So if you use the universal property, so then phi induces a ring map, or basically it's a K algebra homomorphism. So let's write phi induces a K algebra homomorphism. So K algebra homomorphism means it is a ring homomorphism as well as it is a linear map of K vector spaces. So it is a K algebra homomorphism phi bar from R quotient I, sorry, not R, from C of x, y, z quotient I to C of t. So if we prove that, now if we prove that this map is injective, then that we conclude that I is the kernel of phi. So if we can show that phi bar is injective, then uh, we can conclude that uh, kernel, that I is same as kernel of phi. So how to prove that phi bar is injective? So it is a, we will use the fact that it is a K algebra homomorphism, means it is a linear map of K vector spaces, to prove that it is injective. So now note that image of phi is same as image of phi bar. But what is image of phi? So x goes to tq, y goes to t power 4, z goes to t power 5. So the image is basically same as c of tq, t power 4, t power 5. This is also a K vector space, which is a K vector space. Sorry, not K, it's a C vector space. So I am using C here. So it is a C vector space. So what is the basis? So its basis is basically t power n, where n is bigger equals to 3. See, all the monomials are there where monomials t power n is there where n is bigger than 3. Now, can we find a K vector space basis for the left hand side? Now, also observe that in CXYZ modulo I, we have, uh, so we are going modulo by I. So these elements are 0 in this quotient. So we have xz minus y square, this is 0 bar. Then xq minus yz, this is also 0 bar. And x square y minus z square, this is also 0 bar. So that implies the element xz is same as y square, the element xq is same as yz bar, and x square y is same as z square bar. So one thing I will just mention, I will not prove. So then every element, so an arbitrary polynomial is sum of monomials. So an arbitrary monomial in this quotient has this form: x power a, y power b, z power c. So every element, this one in c x y z mod I can be written as C linear combination of elements of type x power n1, x power n2y, and x power n3z for some n1, n2, n3 greater equals to 1. So this type of elements can be written as C linear combination of elements of this type, and these are non-zero elements in this quotient. So our claim is this type of elements forms a basis. So I will put that as an exercise for you to do this. So the exercise is the set x power n1, x power n2y, x power n3z, where this n1, n2, n3 are at least 1. This actually this bar, we need to take bar, means these are quotients, these are elements of the quotient ring. So this set forms a C vector space basis for the quotient ring CXYZ modulo the ideal I. Now we have basis for both side. So how to check if vector space, a linear map, is injective or not? So we need to check that the basis elements are mapping to different basis elements. So also check that the basis elements, so let's take this set as A, the basis elements, okay, the distinct also check that distinct elements of A are mapping to distinct elements of let's take this set as B. So distinct elements of B. So this is also an exercise. So hence phi bar is injective. So hence phi bar is injective, and that will imply uh, I is equals to kernel of phi. So this completes the proof. So by hand this is little bit lengthy and somewhat difficult also, but you can check it via Macaulay 2. These things are easier in Macaulay 2. Okay, so let's do the other problem. Question number 7. So let R be a Noetherian ring. R be a Noetherian ring, and P1 up to PR be prime ideals of R. So be some prime ideals of R. Now suppose radical of an ideal I is same as intersection of these prime ideals I equals to 1 to R. Then so that if you take the set V of I, then it is same as you take the set P1 up to PR of prime ideals and take the Zariski closure. Means take the closure of the set with respect to the Zariski topology. So let's recall the definition of V of I. So V of I is basically the set of all those prime ideals of R such that P contains I. Now recall the property that V of I is same as V of radical of I, and V of radical of I is V of intersection of Pi I equals to 1 to R, and this intersection will be come out as union. So this is V of P of I equals to 1 to R. But this Pi as prime ideals. So this we can write as union of, you take the singleton set Pi and take its Zariski closure. So this is because for any prime ideal P of R, the V of P means the variety of P is same as the Zariski closure of that singleton set P. So this you can try to prove by yourself. So this is the main thing actually, but still it's okay. So this is union of this closure of this singleton sets, but we are having only finitely many of these sets. So this is same as you take the union first and take the closure after that, because we are in finite sets here. So this also easier if we assume this part. So this is Zariski closure. Okay. Okay, the next problem, question number 8. So let R be a Noetherian ring and I be an ideal of R. Now suppose I is equals to intersection J of I equals to 1 to R, be an irreducible primary decomposition, I equals to intersection J of be an irreducible primary decomposition of the ideal I. Then show that for an element A belongs to R, if you take the saturation, so for A belongs to R, so if you take the intersection of of Ji, so here I, you take I such that A does not belongs to radical of Ji. You take all those Ji such that A does not belong to radical of Ji. Then this intersection is an irreducible primary decomposition of I, saturation of I with respect to A. So here you have an ideal I with its irreducible primary decomposition. Then for any arbitrary element of the ring, if you take the saturation, then you can find the irreducible primary decomposition of the saturation from the irreducible primary decomposition of the ideal I. So let's prove this. So I is basically intersection of Ji. I is equals to 1 to R. Now let I colon a power infinity is same as I colon a power m for some positive integer m. So let's take this part first. So then we are given that I is equals to this intersection. So if you take the colon both side, we will get intersection Ji. So we are taking with m. So we are taking intersection in the first slot of the colon. So this is one property of the colon, that it is same as you take the colon first and then take the intersection. So it is Ji. So I equals to 1 to R. But one thing, what is this J colon I power m? So Ji colon a power m, this will be same as r when a is in the radical of ji. So this thing you can check. So for some I, if this colon is r, then we can remove that term because that term is irredundant. So this intersection is same as ji colon a power m. So intersection of all those ji such that a does not belongs to radical of j. So you can prove this part as exercise. But if a does not belongs to radical of ji, then this intersection is same as ji. So I such that a does not belongs to radical of ji. So this is because ji colon a power m is same as j when a does not belongs to radical of ji. And since ji are primary ideals, that is the reason. So this also you can check. So I colon a power m is same as this intersection, and these are primary ideals, and none of these components you can remove because this is a, so here, so this intersection is already irreducible, so you cannot remove any term, and we are taking a sub collection of this thing. This is also irredundant. Hence intersection of ji where I is running from a does not belongs to radical of ji is an irredundant primary decomposition of saturation of I with respect to A. So this is fairly easy if you know the properties of these colons. So try to see this, try to do this, or you can see standard texts. It should be in the standard texts. So this is problem number 8. Okay, now let's do some somewhat easier problems. So problem number 9. So it is basically a true false type question. So it is, if you take the ring k of t square comma tq, the polynomial ring, then this is integrally closed in k round bracket t. So this is true or false. So this ring is integrally closed in this ring or not. We need to check that one. But first we need to know what we mean by integrally closed. So a domain D is integrally, okay, a ring R is integrally closed in a ring S which contains R if no element x belongs to S minus R is integral over R. So here you have S, here you have R. So only elements of S which are integral over R are the elements of R itself. So then we say that R is integrally closed in S. So this you can take as a definition. So we need to check here we have K round bracket T, which is the field of fraction, which is the fraction field. So I will write it here. So if you take the integral domain, the polynomial ring K of T, then its fraction field is K round bracket T, and this contains Kt square over Tq. So we need to check this is integrally closed or not. Now note that T belongs to K round bracket T, but it does not belong to K T square Tq. And also note that T satisfies the polynomial, in fact the monic polynomial x square minus t square tq of x. So t is integral over k t square tq. So an element which is not in the subring but in the bigger ring is integral over the smaller ring. So this cannot be integrally closed. Hence false. So this one is false. So I hope it is clear. So let's do one more problem. So question number 10. So consider the ring map, let's say phi from C x comma y, the polynomial ring in two variables over C, to the polynomial ring over C in variable t, defined by where x is mapping to t and y is mapping to t square. Then how many points does the fiber over the point over this prime ideal, in fact maximal ideal, uh, over the point, sorry, corresponding to this ideal x comma y have. So let's try to understand what does this question means. So we are given a ring map uh, cxy to c of t, which is phi. X goes to t, y goes to t square. Now this ring map will induce a continuous map from spectrum of c of t to the spectrum of c of xy which we usually denote by phi star. And how it is defined: if you take a prime ideal P, then it maps to the inverse image of P. If you take a prime ideal P here, you just take the inverse image here. So this is a continuous map with respect to the Zariski topologies. Now M is an ideal here. So fiber over this point means you take the inverse image phi star M. Then how many? What is the cardinality of this set? So we need to find cardinality of phi star inverse M. So how many elements are there whose pre-image is this? So if you take the maximal ideal, so how many pre-image are there? That we need to find. So basically, here we have M. So what are the prime ideals here which corresponds to this M? That we need to find. So let E belongs to spectrum of CT such that phi star of P is equal to M. But what is phi star P? This is phi inverse P. This is M. And M is ideal generated by x comma y. So that means P is basically subset of phi of M. Sorry. So phi of M is subset of P. So phi of x, phi of y belongs to P. But what is phi of x? It is t and it is t square. These are element of P. So t is in P. That means ideal generated by T subset of P. But in C of T, ideal generated by T is maximal ideal. So ideal generated by T is equals to P. Because this is a maximal ideal in C of T. So there are only one point in the fiber over x comma y. So this completes this solution of this problem. Yeah. This is also not much difficult, but one needs to be careful. So I think I have completed all the parts of this week. So it is better to stop here today. So again, we will meet in the next week.